So do you hear my presentation? Do you see it actually?
Yes.
And do you hear me?
Yes, sir.
Okay, wonderful guys. So as I said, it's about the introduction of multiphase reactors, it's about in particular fluidized bed reactors. So in in any chemical process, either biomass conversion or refinery, petrochemical, even mineral processing, a unit of operation can be classified based on onion model. In other words, based on different layers. So, uh, based on this configuration, unit operations are classified into reactors, separators, heat exchangers, and utilities like water, cooling water, steam, and electricity. And in any chemical process, in the internal layer, in other words, the core or heart of the process are reactors. Okay, so first, when you want to design a chemical process, first you have to think about reactors. After you design reactors, then you have to think about the design of the separators, like distillations, for example, like even condensers, whatever. And then you have to design heat exchangers, and then you have to design the utility system of your chemical process. Okay, but so you see that reactors are really important unit of operations. For example, consider this big scheme of refinery, of a crude oil refinery. So you see the simple crude oil enters the refinery starting from a distillation column, but up to the end, when you produce the final products for different purposes, okay, I mean, before you reach the end point, you can see there are many different processes involved in a crude oil refinery. And in between, there are different sorts of chemical reactors. Some chemical reactors in a crude oil refinery are, for example, listed here for steam cracking, visco reduction, alkylation, catalytic reforming, fluid catalytic cracking, and so on and so forth. And in all these chemical reactors, reactants and catalysts are in different phases. In steam cracking, you have only one phase, so it's a monophase, just gas. But in most of the other chemical processes, you see, you have liquid phase, gas phase, liquid phase. You have liquid phase, gas phase, solid phase, and so on and so forth. Okay, and in all these chemical processes, either you have catalyst or you don't have catalyst. Sometimes catalyst itself is a liquid phase, but most of the time catalysts are in solid phase in heterogeneous systems. But by the way, you can see that chemical processes are, most of them are multi-phase. You don't have monophase. Most of them are multi-phase. And uh, these reactors are in different designs. It could be a tubular, it could be a furnace, it could be in the form of suspension, moving bed, fluidized bed, fixed bed, a slurry, and so on and so forth. So there are different even design for contacting these different phases together. So when we say a multi-phase reactor, as a definition, there are at least two phases moving relative to each other. For example, consider this bubble column. In the bubble column, you have a bed or a tank of liquid. So the liquid is injected through a special spargers or distributors, and the gas also is introduced through uh, spargers and distributors, and make some bubbles so the gas bubbles are in kind of a dispersed phase in the continuous phase of the liquid, and then everything gets mixed, and eventually liquid and gas are the outlets. So you can see that there are two gas and liquid phases in this system. In another multi-phase system, which is the very famous fluid catalytic cracking process for making gasoline. in this process, you have mostly gas and solid phases. So you have a riser. This vertical tube is the riser of the FCC. So the fuel is injected from the bottom. Inside the riser, you have catalyst that is actually returned from a regenerator. So there is a very high gas velocity inside this riser. At the outlet of the riser, the mixture of the solid catalyst and whatever vapors introduced into the cyclones, solid particles are recovered. They are sent to a regenerator, but the products are out from the outlet of the cyclones. And these catalysts that are recovered, they are usually deactivated catalyst particles. They are sent back to a regenerator, which is a fluidized bubbling fluidized reactors. And inside this reactor, uh, air is injected in order to burn off the carbon deposited on the surface of the catalyst. So after catalyst is regenerated, it is sent back to the bottom of the riser. Actually, this FCC is a kind of circulating fluidized reactor. I will talk later, but if you see that there are two phases, solid and gas phases. So it's a type of multi-phase reactor. Talking about
Uh,
catalysts in multi-phase
Professor,
system. Yeah,
I had a question concerning the last slide.
yeah,
Like you said in the riser that some of the solid was entrained in the reactor. Uh, I had to design, I had in part to design some CFB, and we were wondering if you could feel like big chunks of material, or does it have to be reduced in size? Because my theory is that you could put like huge pellets in it, and they're going to decompose slowly, and then the smaller particulate are going to be fluidized with the bed material, or do they have to be small at the beginning?
that's a big question actually.
Sorry.
If you want, I can you can we can set a time later of the class.
Okay, okay.
Definitely, I will explain all details to you. It's a big question because
All right, thank you.
I cannot answer in one sentence, but definitely let me know. Okay, after the class, I will give you more details.
All right, no problem.
One project. So, in terms of catalyst, you have different sorts of catalysts, either in the form of powders or in the form of granulars or kind of needles or pellets. You have different sorts of catalysts in multi-phase systems. But usually in fluidized reactors, we will discuss next. Uh, Solid particles are quite small. I mean, they are less than 1 millimeter. So that's why, as I told Francis, that you have to. It's a big question what we ask. We will see what type of particles usually we deal with in fluidization. So, as a general, most of the multi-phase, especially catalytic reactors, are in the form of fixed bed, moving bed, fluidized bed, circulating fluidized bed, bubble columns, emulated bed, and the star reactors. So, if you want to learn more about them, you have to go to course notes, course books. There are huge number of publications about them. But maybe you want to ask how to characterize and classify reactors. So fluidized bed, bubble column, fixed bed, moving bed, what type of reactor? So the answer is not easy, but there are some typical criteria that you have to identify to select which reactor design you have to take. For example, type of operation, is it a batch system or continuous system? Type of reaction, is it thermal or catalytic? For example, if you have a um, catalytic process where your catalyst gets deactivated fast, fixed bed is not a good idea because you have to regenerate your catalyst. So it's better. So you need to have a system that catalyst can be moved to somewhere else in order to regenerated and then get back to the main reactor. Type of flow phases. If you have single phase, only gas or only liquid, for example, or a combination of different phases, gas liquid, gas solid, gas liquid solid, gas liquid solid solid. When we say solid solid, one solid is usually catalyst, one solid is a reactant. For example, in biomass conversion, you have biomass which is solid, and you can have a solid or as a catalyst as well. Hydrodynamics. If the I mean in hydrodynamics means the flow pattern of the material inside the reactor. Is it a CSTR, polite flow, co-current, or counter-current? The activation rate, the activation of the catalyst, I mean, cycle length, online regeneration, and thermal control. If your process is going to operate like isothermal or adiabatic. So all these questions should be answered to find out which type of reactor you need. But after that, let's now start talking about fluidization. What are the fluidized bed reactors? Fluidized bed reactors are most of the time two-phase system, either gas-solid fluidized beds or liquid-solid fluidized beds. Liquid-solid fluidized beds are mostly, for example, for water treatment, uh, but it's not the topic of our class. We just want to put the focus on gas-solid fluidization. So consider, for example, this kind of column. Okay, at the bottom you have a gas distributor. Okay, and you have put solid particles above the on top of the gas distributor. Okay, and you inject your gas. You inject your gas from the bottom of the distributor, and the gas uh, gets into the distributor, makes some jets, and then jets are converted to bubbles, and then these bubbles uh, apply direct force to the particles, and then all the solid powders move around in the bed like a fluid. That's why we call them fluidized bed. Because at the beginning, particles are just solid, they don't move around, but after a specific gas velocity, particles start to move. So the bed behaves like a fluid. So when we say like fluid, it means that, for example, if you look at this figure, if you incline your reactor, always the surface of the bed is going to be horizontal because it's a fluid. Or if you make a hole on the wall of the reactor, all the powders they tend to get out, to get discharged. Okay, all these are like a fluid behavior. Or if you have two reactors where they have one wall in common, and then and they are at different levels. But for example, this one on the left has a higher level of the bed, and this one has a lower level. But as soon as you make a hole in between, powders, uh, material from the first reactor, they tend to get discharged and transfer into the reactor in the tank on the right until the level at both tanks are equal. And also, if you have a bed, you can easily measure. If you have a pressure transducer, yeah, and you put the one leg of the transducer in um, at one height and another one at the second height, you can easily measure the pressure drop uh, across the bed lengths. So all these behaviors that you see are similar to in the case of, for example, you have just one glass of water, and if you all these behaviors you can see with the glass of water as well. That's why we call them fluidized bed. But fluidized bed reactors essentially they could have different regimes. In other words, they could have different flow patterns. Let's, for example, assume this tank on the left. If you apply a gas with the velocity of Vg, or sometimes people use by show the velocity by U, doesn't matter, Ug or Vg, gas velocity. If you apply a gas velocity very slowly, Um, you might end up in a situation that the still powders are not moving around. The bed is still a fixed bed. Okay, but as soon as you start to increase the gas a little bit, little by little, so if you apply, let's say here is VG1, here is, for example, VG2. If you apply the gas so that VG2 is more than VG1, you can we can you can at some point see a behavior that how there's a start to move around. Okay, so the bed height, if for example at the beginning in the fixed condition, if the air is 0, okay, at some point you can see that H1, the level of the bed has increased, is more than H0. Okay, and and if you again increase the gas velocity, you reach a point that not only powders uh, they have started to move around, but also you clearly see some bubbles are formed. So when bubbles are formed, we call it the fluidized bed is like a bubbling fluidized bed or bubbling fluidization. But I have to just clarify something. You will see later that powders are classified in four categories: Group A, Group B, Group C, and Group D. If you are using Group A powders, you will see later what kind of powder they are. Always, these two systems are very distinctive. In other words, when the particles start to move up or move around, you don't see a bubble, okay? But at some point, at another level of gas velocity, you see the bubbles. So the velocity associated with this bed, we call it UMF, minimum fluidization velocity, a velocity at which the particles started to move around, and the velocity at which you start to observe some bubbles, we call it minimum bubbling velocity. Okay, so always minimum bubbling velocity is more than minimum fluidization velocity. And these two distinctive velocities are characteristic of group A powders. But when you are dealing with group B powders, UMF and UMB are similar. They are the same. In other words, when you are dealing with the uh, group B powders, as soon as the direct force applied by the gas, okay, is just enough to uh, move the particles around, in other words, the bed becomes fluidized, you also see formation of bubbles. So these bubbles that are formed, uh, they start right after powder become fluidized. But regardless of the group A or group B, if you increase the gas velocity even more, you observe a kind of turbulent fluidization. In turbulent fluidization, the shape of the bubbles is not the shape that you see in the bubbling fluidization regime. The bubbles are kind of elongated uh, bubbles, and you have a very intense mixing of the gas and solid. And if you increase the gas velocity even higher, you end up with a very fast fluidization condition, or we call it circulating fluidization. In a circulating fluidization, you have always a middle zone where concentration of the gas is more than concentration of solids, but close to the wall of the fluidization, concentration of the solids is more than concentration of the gas. So this is the characteristic of the fast fluidized beds. So fast fluidized beds are gas velocity in fast fluidized beds is more than gas velocity in turbulent. But you have another configuration of fluid as well reactor that we call it pneumatic transport regime. In these systems, the gas velocity UG is much more than gas velocity in circulating fluid as bed, so that you end up with a situation that concentration of the solid is almost 90 to 95% of the bed. So, sorry, concentration of the gas. So solid concentration is really low. So if you compare a fixed bed to transport fluidized bed, you can see, if you look at the concentration of the solids, you see that in fixed bed you have a very dense um, concentration of the solids, but in transportation regime, concentration of solid is very dilute, is very low. So you have different fluidization regime with respect to gas velocity. Okay, but a typical fluidized bed reactor is shown here. It's just a very typical. So of course, first you have the main physical body of the fluidized bed reactor. You have a distributor in order to distribute the gas to maintain the fluidization. So the gas can be heated in a furnace or in a heater, and then introduced into the reactor to make the bubbles and move the particles around to make them fluidize. And the feedstock, for example, biomass, could be added to a screw feeder to be fed into the reactor, either from the top or from the middle, depends. And if your system is exothermic, maybe you need to have a heat exchanger, or I mean a coolant, in order to fix temperature inside the fluidized bed. You need to have a cyclone, gas solid cyclone, in order to capture solid particles that are inflamed by the gas and get them back to the bed through the deep leg. This pipe is called deep leg. And then the exit gas uh, is out, and if the exit gas still contains some solids, you might use a secondary cyclone chain in order to recover the solid, and they have the final gas in the outlet of the cyclone. And this is a typical fluidized bed reactor. But definitely there are advantages with fluidization, especially because of the solid handling. It's very easy to add and remove solids. You will have rapid solid mixing, so you can maintain a kind of isothermal condition. But the most important uh, advantage of fluidization are really high heat and mass transfer rate between gas and particles. And this is the most important advantage of fluidization. So you will use less energy, for example, because heat transfer coefficient is quite high in fluidization. But definitely there are disadvantages in fluidization as well. For example, you know, um, see, because fluidized beds, their behavior is like a CSTR. They are not CSTR reactor. CSTR are kind of ideal reactors, but their behavior could be considered like a CSTR. So usually, for a specific volume, the conversion of in fluidized beds is less than conversion that you can obtain in a pellet flow reactor. Okay, and you could have a kind of non-uniform residence time of solids in the reactor, but I can say that some of the most important problems with fluidized beds are attrition of particles. I mean, for example, if you have catalyst particles that are not mechanically strong, since particles always they collide each other, they touch each other, they could break out, and you end up with the smaller particles, and at the end you might lose your catalysts that are expensive material in the outlet of the reactor. And if you have pipes, for example, heat exchangers and other vessels inside, like a cyclone, they could be eroded because of the particles that are hitting the surface of these pipes and vessels. And also, you might end up with the agglomeration of the particles. So, specifically, for example, in biomass gasification or biomass combustion, uh, you end up with the situation that uh, your since, for example, in biomass you have ash, and this ash material could melt and they could behave like a binder between two particles. So at the end, uh, particles in gasification reactor could stick together, and at the end, you end up with a big chunk of, let's say, like a stone, and the bed is like a dead. It's not fluidized anymore. We call it a defluidization situation. So there could be disadvantages. So definitely, engineers who are expert in fluidization, they know how to manage this kind of issues. So, two important fluidized best in the industry. I just want to give you an introduction. One of them is FCC, as I discussed before, fluid catalytic cracking. So you can see how this unit looks like in a refinery. So fluid catalytic cracking is the main reactor to make gasoline. Majority of the gasoline that is produced is by FCC reactors. But another type of fluidized beds are for combustions, either coal combustion or biomass conversion. For example, consider this fluidized bed reactor. You can see that in this case, for example, coal is prepared and then mixed with limestone, and then by a screw feeder is injected to the bottom of the fluidized bed reactor. You know that in combustion, the main reason that we do combustion is to generate energy. So due to the energy released by combustion, you end up with producing superheat steams. Okay, so there are pipes of the steam passing through the upper part of the reactor. So as soon as the gases reach the pipes, heat transfer occurs and heat the way and the steam will be converted to superheat steam. And anyway, all the gas vapors and particles at the top, they go into a cyclone. Non-converted coal, for example, is going to be collected and returned to the fluidization or fluidized bed combustor, and the remaining gases they go to other cyclones where ash material, we call them fly ash, are going to be recovered, and the remaining gases like, for example, um, CO, CO2, NOx, SOx, they are going to be uh, released to atmosphere. Of course, from environmental point of view, there are ways to control their emissions. Okay, now let's talk a little bit about some fundamentals of fluidization. Maybe this is very basic information, but it's extremely important. There is a very famous guy that died recently. His name is Geldar. Geldar is one of the godfathers in fluidization. He classified particles in four groups: Group C, Group A, Group B, and Group D. Group C is used because it's for very cohesive particles. Usually particles that are very fine nanoparticles or particles with less than roughly 50 micron. They are very sticky particles. And by the way, okay, and also group B particles, in opposite to group C, are usually quite large particles. Roughly size of group B particles is more than 1 millimeter and 2 millimeter. And group A, group B powders, they are usually powders that are used in conventional fluidized reactors, and their size particles usually they have a size something between 50 micron to 1 millimeter roughly. But of course nowadays there are fluidized bed reactors designed for fluidizing even cohesive particles, group C Gelder particles. But if you want to understand how they are classified, it's really based on density uh, of the particles minus density of the fluid. Gas solid system fluid is a gas, so it's based on the density of the phases and average particle size of the particles in the bed. So as you can see, for example, when you have very small particles, less than, for example, in this zone, you can see, uh, depending on the particles density, especially if your particles are, they have density below 2000 kilogram per square meter and size below 50 micron, they are part of group C. And group D particles, you can see, if you look at this region, you can see that usually particles have size more than 1000 micron or 1 millimeter, and density is usually more than 2000. So in this region, you can really identify a specific particles density and particle size um, impact on classification of the particles. And group A, group P are in between, as I said. So really by looking at this graph, by knowing density of the particles, density of the gas, also average particle size of the average size of the particles, you can identify which group your particles belong to. So back to Francis' question, you know, you need to have an idea if your materials for fluidization are group C, group A, group B, or group D, because uh, fluidization of group C and group D is a big challenge. Usually for group D particles, for example, use ebullited beds, uh, but for group A and group B, fluidization is quite known and very not easy, but it's something that has been practiced commercially. So uh, let me tell you something a little bit. If you remember, by the way, if you remember, I said in fluidization you have different regimes from fixed bed regime up to transportation regime. But something that is practiced by fluidization engineers is always to control the height of the bed versus pressure drop. Is very important because if your height of the bed is too high, you may lose your material, and if it is too low, you don't have a good uh, reaction performance. So it's always important to have an idea of the bed height. And to measure the bed height, you use usually pressure drop along the reactor. But also, you have to measure the pressure drop delta P in order to make sure that your reactor is fluidized. Okay, and let's now move together to really monitor uh, delta P across the bed height and H, which is the height of the bed, while you are increasing the gas velocity. We show it by SVSG, but it's just gas velocity. So let's say at the beginning gas velocity is zero, but uh, it is always very observable. You can easily observe that when you increase the gas velocity up to some level, even though you increase the gas velocity, your pressure drop increases, but the bed level H, the blue color is about the bed H. That's why y-axis is shown by a blue color. Red is used for delta P. You can see that when you start to increase the gas velocity, pressure drop increases, but the bed level is fixed. It's a characteristic of the fixed bed reactors. Okay, so you know Ergon equation, I'm sure, in your transport phenomena. But so you can use the ergon equation to calculate also what is the delta P of the reactor, a cluster reactor. But if you have pressure transducer, for example, you can compare this delta P with delta P that you calculate from ergon equation. But let's say that you increase the gas velocity a little bit more. You end up with a point where uh, you reach UMF or VMF, minimum fluidization velocity. Okay, and at this point, it's very interesting. At this point, bed height starts to increase. So if you increase the gas velocity even more than UMF or VMF, bed height increases. But something interesting happens to delta P. Delta P of the reactor uh, increased up to a certain point. Okay, and after that, after after UMF or VMF here, delta P drops again. Okay, so this is a very characteristic of especially uh, FCC particles, because FCC particles are usually group A particles. If you remember, we said with group A particles, you have minimum fluidization velocity and minimum bubbling velocity that are two different numbers. So usually for FCC, VMF is between 1 to 3 millimeter per second. I mean the minimum friction velocity. And this VMF can be calculated from this equation where you have Archimedes number, and this Archimedes number is a function of size of the particles, density of the particle, density of gas, and viscosity of the gas. And interestingly, if you increase the gas velocity above VMF, as I said, you end up with the with VMB, minimum bubbling velocity. So at this velocity, you start to observe bubbles in the reactor. But if you follow delta P, you see that delta P at VMB a little bit increases, but then it starts to be almost plateau. Okay, almost. Okay, and uh, bed height, we can see that the bed height is also a little bit plateau, but with very slight increase. And if you want to have an idea about these two values, you can use this equation. By knowing the VMF, you can have an idea what should be the VMB, what minimum bubbling velocity. Typically, when the bed starts to be fluidized, gas holdup is between 50% to 60%. I mean, gas holdup, I mean, fraction of the bed occupied by gas. But uh, in something is important is about uh, uh, we say turbulent velocity (VC). When you reach the VC turbulent velocity, the bed height starts to drastically increase, but the delta P of the bed starts to drastically decrease. These are the characteristics of uh, bed height and pressure drop in turbulent regime. Usually in turbulent regime, uh, uh, gas holdup is between 60% to 75%. And if you want to measure the epsilon, you can easily use this simple equation by knowing the gas velocity. You can have an idea what is the uh, bed voidage. But you can see that in turbulent regime, your bubbles are kind of elongated, and since you have very high gas velocity, definitely you need to put a cyclone inside the reactor to recover inflamed particles. Okay, I hope you could get an idea about characteristics of of the fluidization versus gas velocity, and how the delta P of the bed and height of the bed inside change by just increasing the gas velocity. But let's say you are just new in fluidization, or you are just designing a fluidized bed reactor, and you want to just have a very simple method to find out uh, the delta P of the reactor, and to find out what is the height of the of your reactor of your fluidized bed reactor. It's very simple. So if you put a couple of pressure transducers, so that, for example, in this case, we have three pressure transducers having legs, having the legs of the both inside the fluidized bed, but the other two pressure transducers, so that each has one leg inside the bed, but another leg above the surface of the fluidized bed, and you measure the delta P, you end up with these readings. Okay. In other words, you see that uh, always delta P is increases at higher levels. Okay, but as soon as your one leg of the transducer is above the surface, the edge doesn't change. Okay, sorry, the delta P doesn't change versus the height. So you can have easily these readings. So by plotting these as easy lines, you can find this cross section and then find what is the edge of the reactor. So by just this very easy, simple method, you can measure the delta P. You can measure height of the reactor. By knowing the height of the reactor, okay, since we know that delta P is can be also calculated by density of the bed by G and height of the bed. Let me show you this H by this one. By obtaining this value, you can also obtain a density of the bed, because this is a very important parameter in fluidization to have an idea what is the density of the bed. But in other words, uh, I mean, there is another technique to measure the bed level. If you don't want to put five pressure transducers and just use only two pressure transducers, so it's very easy. You can have one pressure transducers with two legs inside the bed. Okay, so uh, by measuring delta P1, okay, and having this equation, you can measure density of the bed. Lit in French is the French word. Is the in English we say bed. Density of the bed can be obtained by knowing by measurement of the delta P1. Okay, and by using the second pressure transducers, you can calculate delta P2. Already you have calculated uh, density of the bed by delta P1. Then using this equation, you can calculate H as height of the fluidized bed. So these are some very simple methods to measure delta P, or to measure level of the fluidized bed reactors. So this was very simple. I mean, introduction to fluidized bed reactors. I hope you could get some ideas. What are the most important parameters in fluidization? As I said, the most uh, important uh, parameter in gas solid fluidized bed reactors is really classification of particles. You need to have an idea of what group your particles belong to. After knowing your group of the particles, then you need to uh, uh, go to the course notes or design books to find out different procedures to design your reactor. Okay, but as I said, I'm going to give this course in summer if somebody was interested. But it was important for you today to uh, have an idea of fluidization because uh, otherwise, when you study pyrolysis, gasification, combustion, even fluidized bed drying, you don't really know what are the most important things inside the fluidization. But again, also, I forgot to tell you something. Another parameter, important parameter in fluidization, beside type of the particles, is really gas velocity. In fluidization, we don't talk about gas flow rate. Mostly, we talk about gas velocity. That's why we always talk about minimum fluidization velocity and minimum bubbling velocity. And again, as I said, in group A powders, UMB and UMF are different values, but for group B particles, minimum fluidization velocity and minimum bubbling velocity are two similar numbers. Okay, I hope you could get some ideas about fluidizer reactors. So let me stop recording.